Hello class, welcome back to my YouTube channel, and for today I'll be your teacher in General Mathematics, and we are going to discuss the lesson 18, which is about representing real-life situations using logarithm functions. So from our previous discussions, we have already discussed the rational functions, the exponential functions, the inverse function of the rational function and one-to-one function, and also now we have the logarithmic functions, which is the inverse of the exponential function. So first, let's define what we mean by logarithm. So it is the inverse function of exponentiation. So as I've said earlier, the logarithmic function is an inverse function of exponential function. So let's say we have let A and B be positive numbers such that your B is not equals to 1. So our B here is the base and our A is the power. So the logarithm of A with base B is denoted by log with the base B power of A, which is defined as the number such that your B raised to, the exponent will be log base B A is equals to A. That is the exponent that B must be raised to produce an A. So this means that if we raise the logarithm as the exponent of the base, the answer will be the power or the A. So we have here the exponential form and the logarithmic form of the different expressions. So we have the form B raised to C or base raised to C, which C is the exponent, which is equals to A. This is the form of our exponential. So we've already encountered that from our previous topic. And now, the counterpart or the inverse of that exponential form will be the logarithmic form. So this is the form logarithmic B, log B, base B, this one is also the base, power of A, so that is equals to the exponent C. So let's have examples. We have here exponential form 2 raised to B, 2 raised to 5, sorry. So we have 2 as the base and our exponent here is 5. So we have 5 times 2 times 2 times 2 times 2 times 2, that is equals to 32. And in the logarithmic form, we have log base 2 power of 32 equals to 5. So our exponent here is 5, the base is 2, and the answer to 2 raised to 5, that is equals to the power 32. Another example, we have 9 cubed or 9 raised to 3, that is equals to 729. That is in exponential form. So when we're going to transform it in logarithmic form, we have log base 9 power 729 equals to 3. Fourth example, we have 1/2 as our base raised to negative 4. So the exponent here is negative 4 in exponential form. That is equals to 16. So why it becomes 16? So this exponential equation shows the law of negative exponents. So when we distribute this negative 4 as the exponent of positive 1, that will be still 1. And when we raise 2 to negative 4, that will be 2 raised to negative 4. So since it's in the denominator, we can get the reciprocal to eliminate the negative sign of the exponent. So that will become part of the numerator. So when we transform it into the numerator, we'll have here equals to 2 raised to 4. So 2 raised to 4 is also equals to 16. How? We have 2 times 2, that is 4, times 2, 4 times 2, that is 8, times 2, that is equals to 16. That's why we have equals to 16 here. And in logarithmic form, when we transform it, in logarithmic form, we have log base 1/2, 16 equals to negative 4. Now, on the last example, we have 7 raised to 0. So anything that we raise to 0, if your exponent is 0 in any expression or in any constant, will have an equals to 1. So we have equals to 1 here. Next, in logarithmic form, we have log base 7 power of 1 equals to 0. So since our exponent is 0, so we have equals to 0. So now, we need to remember the following statement. So in both the logarithmic and exponential forms, b is the base. So don't forget that your b is the base. In the exponential form, c is an exponent, but c is equals to log b a. This simplifies that the logarithm is an exponent. So your logarithm is just equals to your exponent. So that log base b power of a is equals to your c, which is the exponent. In logarithm form, log base b a cannot be negative. So we need to remember that your a or your power should not be a negative value. It cannot be a negative value. And last, the value of log b of a can be negative. So your power cannot be negative, but your exponent can be negative. So the value of log b a is your exponent or your c. So it can be a negative value. So we have this called common logarithms. What is this? So common logarithms are the logarithms with base 10. The base 10 is usually omitted or removed when writing common logarithms. So we have here log base 10 of x equals to log of x. Simply, it becomes log x. So that is called the common logarithms. So don't forget that your base is 10. Another, we have the natural logarithms. What are these? So these are logarithms with base e. So it is denoted by ln. What is this e? So your e is equals to 2.71828 approximately. So if you have a scientific calculator, you can find the approximation, the value of the e, which is the base of our natural logarithm. So it is denoted by ln of x, which is also equals to log base e of x. So again, our e, the approximation value is 2.71828. Now, let's have examples. So first, we need to rewrite the following exponential equations in logarithmic form. So we have first 5 raised to 3 or 5 cubed equals to 125. So how it becomes 125? So we have 5 times 5 rather. 5 times 5, that is equals to 25. So your 25 multiplied by another 5, that is equals to 125. So the answer here in logarithmic form, it will become log base 5, our base here is 5, and our exponent is equals to 3, and then the power is 125. So we have log base 5, 125 equals to 3. Another example, we have 10 squared equals to 100. So 10 times 10, that is 100. So the logarithmic form is log base 10. So our base here is 10. So it is omitted already. So we can just neglect writing it. So we have log 100 equals to 2. Now, last example, we have e raised to 5 equals to x. So we know that if we have a base e, we have a natural logarithm. So the answer here is ln of x. So our power here is x. So we have ln of x equals to 5. So 5 is our exponent. And now, let's have examples. Again, this time, we need to rewrite the following logarithmic equations in exponential form. So, in letter A, we have exponential to logarithmic. Now, we have logarithmic to. So, first example, we have log m equals to n. So, we don't see any base here. So, meaning our base is equals to 10. So when we don't write the base, that means the logarithmic has a base 10, which means it is a common logarithm. So this one is an example of common logarithm. Now, log m is equals to n. Let's transform it in exponential form. So the answer is our base is 10 raised to n, because our exponent here is n rather, and that is equals to power m. Second example, we have log base 3/4 or 3 over 4. The power is 64 over 27 equals to negative 3. So our exponent is negative 3 and the base is 3 over 4. When we raise 3 over 4 to negative 3, the answer will be 64 over 27. It becomes the reciprocal of 3/4 raised to 3. So we have 4 raised to 3, that is 64, and 3 raised to 3, that is equals to 27. When we transform or rewrite it in exponential form, we have 3/4 raised to negative 3 equals to 64 over 27. And last, we have ln 8 equals to a. So when we have ln, or the natural logarithm, our base is e. So we have e raised to a, that is our exponent a, equals to 8, which is a power. Now, let's have the applications of logarithm. So if we're going to apply the logarithms, logarithms helps us interpret large numbers. So one of the applications in real life, we have the earthquake magnitude on a richer scale. So when we have magnitude of an earthquake, it is defined in a small value, but it nearly a very large value. It's just we are representing it in logarithm. So we have an earthquake magnitude on Richter scale. The Richter scale is the one that measures the earthquake magnitude, but it is measuring the intensity. So this Richter scale is the one that was proposed by Charles Richter, and it helps to define the magnitude of an earthquake as a function of its amplitude on a standard seismograph. So the formula to be used is based on the energy released by the earthquake. So magnitude and intensity of the earthquake were measured by the seismograph on a Richter scale. So the magnitude R of an earthquake is given by this formula. So our formula here is R is equals to 2/3 log E over 10 raised to 4.4. So our intensity or the earthquake energy is represented as E. And this value 10 point raised to 4.4 is the reference, the quantity that is released, the quantity of the energy that was released by a small reference earthquake. So we are trying to have on a Richter scale, we have a reference value for the earthquake energy, earthquake representation of energy. So let's have an example of how can we use the Richter scale in getting the magnitude of an earthquake. So when we heard news, we just heard that the magnitude of the current earthquake according to the P box. So we have magnitude 6, magnitude 7, magnitude 4, 4.4, and so on. So suppose that example problem we have, suppose that an earthquake released an approximately 10 raised to 12 joules of energy. So this 10 raised to 12 is a very large number. So we are going to represent that energy of the earthquake, the energy released by the earthquake, in a logarithmic form using a Richter scale, using the formula. So first question we have, what is the magnitude on a Richter scale? What is the magnitude of the earthquake on a Richter scale? So we have the formula. So R is equals to 2/3 log E, the energy, over 10 raised to 4.4. So substituting our energy, approximate energy here, 10 raised to 12, we have 2 over 3 times log 10 raised to 12 over 10 raised to 4.4. And we have 2 over thirds log 10 raised to 7.6. So when we divide 10 raised to 12 to 10 raised to 4.4, that is equals to 10 raised to 7.6. So the answer will be turn to 2/3 times 7.6. How it becomes 7.6? So the logarithmic involves here is a common logarithm, meaning the base is 10. So we have a base 10 here and another base, the power is 10. So we are going to discuss it further in our succeeding topics. We have a property that is, if we have same base and your power has an exponent involved and your base there is equals to the base of your logarithm, that means the exponent involved there will become the equivalent of this common logarithm or the logarithm. So we have 2/3 times 7.6, and 2/3 times 7.6, that is equals to 5.1. Another question involves in this problem, we have to know how much more energy does this earthquake release than that by the reference earthquake. So we have a reference the energy release has a reference of 10 raised to 4.4. So how much? We have 10 raised to 12 divided by 10 raised to 4.4. So we've already computed that. That is 10 raised to 7.6, which is approximately a very large number also, equals to 39810717. So this means that this value is the number of times more energy than by the reference earthquake energy.